Thank you for coming to my talk. This is work with Aishwarya, Piotr, who are PhD students of mine. I'm a computer scientist. And Alex and Olu are psychiatrists in the medical school. So, this is interdisciplinary work. So I'm going to talk about consciousness as a control or coordination mechanism in a competitive environment. There's been quite a few presentations here and also papers on consciousness as control. And Manuel here and the Blum family if you can look at the workspace model as being some kind of a control or coordination mechanism coordinating the competing processors. So I'm going to talk about also control and coordination, and in my setup, these things are going to be very precisely measurable. Okay. In other words, the amount of control or coordination and the consequently the consciousness, if the connection is being made, it's going to be very quantitative. So in terms of the outline of my talk, first, I'm going to talk about competition and coordination in traffic analysis, in transportation, the traffic system that you see out there in the road, okay, in any major city. Then I'm going to translate this into competition and coordination in brain traffic, which is, again, as I said, amenable to measurement. And then I'm going to discuss some surprising experimental results. And then, in terms of future work, some very speculative ideas in terms of building a conscious robot. How would we do it using this mechanism if it really turns out to be correlated with consciousness? To build this robot, and how would we check whether it's, what would we verify, whether it's a measurement of consciousness. So the red bullet is going to be the first one. So how many people here are familiar with the notion of system optimum versus user equilibrium? It's a game theoretic notion. Okay, people are not. Okay, I'm going to try to suppose this is Pigu's example from maybe 150 years ago. Suppose you have a source and a destination, and you have 3,600 vehicles that are trying to go from source to destination. Okay. And there are two routes from the source to the destination. The top route depends on the congestion. So the more vehicles that are choosing this route, the slower it's going to be. And the second route has 100 lanes, and regardless of how many vehicles choose it, it's going to take 1 hour. Okay. Now, each vehicle, and the vehicles, they know this. The drivers of these vehicles know this. So each one will, in his or her own mind, will say, even if everybody else goes the top route, it's going to be 1 hour. It's not beneficial for me to take the south route, the bottom route. So everybody's going to go through this calculation, and everybody's going to take the top route, and it's going to take 1 hour from them to go from the source to the destination. However, if there is a coordinator, and the coordinator can tell, you know what, 1,800 vehicles go the top route, and 1,800 vehicles go the bottom route, then it's easy. I mean, then the overall, so some of the vehicles will take half an hour, some of the vehicles will take an hour on average. The travel time will be 3/4, and it can be shown that this is optimum, okay, in this particular case. So in the case there is no coordinator, this is the user equilibrium. If there is a coordinator, this is a system optimum. Okay. Okay. Now, transportation authorities in any major city, if they want to build a new road or something, they want to see what would be the impact. So they have what is called traffic assignment software. And traffic assignment basically says everybody wants if everybody wants to maximize their own benefit, their own travel time, then the system will fall into a user equilibrium. So what they do, they have this software in which they feed the road network, and they also feed the demand for transportation. So, for example, Chicago is divided into 3,000 regions, and you have a matrix which gives you for each source and each destination how many vehicles a day go from the source to the destination. Okay, so this way and now they can do it. This software can do it. Either you can do this traffic assignment in a system optimum way, or you can do this traffic assignment in a user equilibrium way. And there are, maybe I'll talk about it at the end, there are some ways in which you can convert the user equilibrium into a system optimum. Okay, for example, using tolling. So the bottom, to give you the punchline of this whole talk, we use this software in connectomics, and I'll explain how we made this connection between traffic and connectomics. I don't, how many people here are familiar with connectomics? Okay. So I'll explain. So we use this in order to determine whether the traffic is closer to the user equilibrium or to the system optimum, and we discovered that the traffic is closer to the system optimum. And this is the surprising result here, because if every signal, okay, has a, maybe I'm trying to, that I'm giving you the punchline. I'll explain more details as I go along. Okay, so you can, in other words, what I'm trying to show you here is that you can tell by measuring how many vehicles are going through each one of these nodes. You can measure whether the system overall is in a user equilibrium or in a system optimum state. Okay, so now let me talk about this competition and coordination in brain traffic. So in connectomics, you talk about structural connectome, which is equivalent to the road network. It's the at the fine level, it's the neurons and the synapses between the neurons. We don't measure it at this level, but just to think about it, this is the structural connectome, and the functional connectome is the firings of the neurons. This is the traffic. Okay, so first, right, so the vehicles are the signals. Another thing to observe is in traffic, right, each vehicle has a origin and a destination. And similarly, right, when I think about raising my arm, then a signal goes from my brain to my muscle and my arm goes up. So there is a source and destination in connectomics, in these firings as well. And in addition, there is also the notion of congestion, which is necessary for applying this methodology. And the issue of congestion arises because after firing, each neuron goes into a refractory state for a short period of time during which it cannot fire. So if there are many signals that go through the same region in the brain, then the traffic will be slower. Okay. In terms of there are 100 billion neurons, 100 trillion synapses, and the neuron can fire 5 to 50 times a second. Now, we don't measure it. You cannot. Connectomics doesn't go to the level of individual neurons, but the psychiatrists that we worked with divided the brain into I forgot, so I think 80 something regions, okay, and using using fMRI, you can detect in other words, how many fibers go between every pair of regions, and this is the capacity of the road network, so to speak. So, right, the weights of the edges. So we build this graph of the structural connectome where the weights of the edges represent the number of neural tracts between voxels and the capacity of each edge. And then using, again, fMRI with slightly different capabilities, you can determine what is the amount of traffic between every pair of regions. You can determine the correlation between when the region is up versus when the region is down. And it is well accepted in brain imaging that this the correlation between the two brain regions corresponds to the amount of traffic between the two brain regions. Okay. Now, the structural connectome is person-specific and evolves slowly over time, and this is clear. And then the functional connectome is more task-specific and is also person-specific, and it changes very much more often than the structural connectome. Okay, so now it's pretty clear what we did. We took this. We took the structural connectome as the road network. We took the functional connectome as this demand, it's called the demand matrix, or in transportation that I talked about. And we assigned the traffic. We said, let's assign the traffic. You can do it either in a system optimum way or in a user equilibrium way. There's quite a lot of calibration here that I don't have the time to talk about. Sometimes there are negative correlations. About 10% are negative correlations. I won't have the time to get into this. But I mean, I would say like similarly to the way you want to get to your destination as fast as you can, then I'm assuming we assumed initially that each signal wants to get to its destination as fast as it could, and therefore the system will settle into a user equilibrium, okay? Which is probably favored by evolution. Okay, what we discovered is that actually the system is not exactly the system optimum, but is closer to the system optimum than to the user equilibrium. I'll get into details, and I want to point out also that system optimum here means, in addition to overall minimum amount of time, or on average, it also implies energy minimality. Okay. So the boy. Anyway, you can measure whether the system is is by measuring the traffic at each one of the nodes, which are the brain regions. You can determine first of all, you can determine what is the user equilibrium, you can determine what is the system optimum, and you can determine also what is the actual traffic. So basically, for the user equilibrium assignment, you have, so we had 87 nodes, which is 87 regions. So for the user equilibrium, you get some traffic in each one of these nodes. For the system optimum, you also get some traffic in each one of these nodes. And as I showed you before, I could go back to the slide, but I don't have the time. But these two will be different. And so this one additional measurement that we used here is that what is the actual traffic in each one of the nodes. And the results are, we took the Euclidean distance, we look at it as an 87, which is the number of regions, 87 dimensional space. And we look at the actual traffic as a point in this 87 dimensional space. We looked at the system optimum as a point in this 87 dimensional space. And system optimum and user. So we have basically the actual traffic, system optimum traffic, and user equilibrium traffic. And we discovered that the actual traffic is closer to the system optimum than to the user equilibrium. Okay. And since we worked with psychiatrists, they did this parcellation and this they did the brain imaging that we use. They have controls, and they have depressed people. They are treating depressed people, so they have connectomes of depressed people and controls, which are the normal ones. So let's, in terms of, first of all, the normal ones, here are the probability of the null hypothesis is less than 5%. In other words, in a statistically significant way, the traffic is closer to, across the normal subjects, the traffic is closer to the system optimum. Across the depressed subjects, it's unclear. Okay, it's inconclusive. Okay, and our conjecture, if we can find the connectomes of unconscious people, and I talked to some people here if we can find the connectomes of unconscious people, our conjecture is that they will be closer to the user equilibrium. Okay, and so what does this give you? So in terms of, first of all, we would like to prove or disprove this conjecture that the consciousness is related to optimality. There is some sense of control that we get when being conscious, and which may mean this exactly the type of control of traffic that I was talking about. So our objective now is to get the connectomes of unconscious people and verify if it's indeed closer to the user equilibrium. Now, if it's disproven, then back to the drawing board. Okay. Now, suppose that it's proven. Suppose that it is true. How we go from this to building a conscious robot, for example. In other words, consciousness would mean control of this brain traffic or whatever, neural network traffic or whatever, so that it behaves in an optimal way, either in terms of energy or time or something like this. So first of all, we will have to find how does the brain control the traffic so indeed in in conscious normal subject, it's closer to the system optimum. Now, suppose that we found this out, how the brain does it. Like I said, in traffic, you can do it by tolling, for example. Tolling is if you have a toll road, that's a mechanism to move the system from system optimum, from user equilibrium towards system optimum. Okay. We can go into why that is, but okay. So now, in contrast, now there is still a possibility that consciousness is just an epiphenomenon. It's not, in other words, the control of this traffic is not, it's an epiphenomenon of consciousness, but it's not what produces consciousness. So now here so how would we produce conscious machines? First of all, if you have suppose you have some chat GPT that you embodied and you put it in a robot, okay? Right. So first of all, using what we learned in the brain, we would see if we can optimize the traffic in this ChatGPT embodied ChatGPT neural network. If we can embody while preserving the functionality of ChatGPT, okay? And then, if so, then suppose you have an embedded robot with ChatGPT capability. How do you know that it's conscious? So what I'm saying, how would you know? So what I'm saying is there is another principle that we are currently looking into, which is the truthfulness supremacy principle. In other words, if you can build a conscious robot, can you build a robot that is not going to lie in any case? Okay, so in order to survive, it may have to lie. Well, this robot, if it obeys this truthfulness supremacy principle, then it's going to prefer to die rather than lie. Now, if this is the case, what I'm claiming is that you can ask the robot, are you conscious? And if it says yes, then the answer is that you have built a robot with consciousness. Okay.